So, I mean, I want to touch on that hardware versus software optimization piece. So we're seeing, FPGAs, ASICs, some specialized hardware companies trying to find those single order of magnitude efficiency gains there. I guess, could you explain why you're more interested in the software optimization side, if that is the correct interpretation, and what some of those trade-offs are? I will touch on trusted and untrusted setups later, but I thought this would be a good starting point.
But software, I mean, maybe we can distinguish two things. One thing is, let's say, mathematical improvements. I mean, you do a new proving system that you do the things in maybe using lattices or using some other hash system. I mean, this is something that's more mathematical. Here, of course, there is improvements and there is research in that front. This is one thing. The other is just software engineering. I mean, you can do the things, but you can do a good code or a code that's more optimal or less optimal. And this is, this is important because, it takes more time or it's more costly on that. One of the things that, and this is one of the things that we are seeing, we are trying, at this point, we are trying to, okay, how fast can we prove an Ethereum block? This is the question, is currently with the current technology, just put as many servers as you want, but how fast you want to, and we see that, we can prove clearly blocks in real time. We're already doing that. So it's doable, okay? So the matter is more about cost, okay? But what's the cost? Maybe you need 100 servers, and these 100 servers cost X. Can you do it in 50 servers? Or instead of using normal CPUs, can you use GPUs or hardware specialized? The problem of specialized hardware is that there is an investment there, okay? And it's a cost of investment. And also the proving systems has been evolving. They are quite new on that, so it needs some time first to stabilize the software, the technology, and then there is an investment, and this investment takes it's a huge capex, and then it takes some time. It would take maybe some time then to amortize on that. Well, this is what's happening. There is some companies that right now are investing very hard on that side, and we hope that this will help a lot in reducing continue reducing the cost of the ZK. But they are coming.
Yeah, I think the way we were thinking about this is we launched to mainnet, I guess, of the order of 2.5 years or so ago now, with the first version of the proof system. The next year we had another version of the proof system. We're now going through an upgrade with another version of the proof system. So, committing to hardware that would be coupled to the proof system would clearly be premature for us, right? At the moment, it's very clear that retaining optionality over the evolution, coming back to how quickly we're seeing progress in the field, the GPUs make sense. But obviously it makes sense that this is an area that other teams are focusing on because they can kind of see where things are going. Just for us, it's not the thing, right? We're moving quite quickly. And then for us on the software side, the trick is really how do you get incredibly high hardware utilization, right? You're running a big GPU cluster, you want to run super efficiently. This is all just a software problem. As a function of the load on the systems increasing, the number of GPUs you have to run increases. You start maybe to think about decentralizing your GPU clusters. These are interesting and non-trivial software problems. But at least for us, the optionality with GPUs is clearly the right choice at the moment.
Just I agree. It's better to stick. It's not time to commit yet. At least we're seeing that as well.
I guess last question on this kind of general topic. Do you guys see any major trade-offs when looking at different trusted versus untrusted setups, especially as it would pertain to kind of efficiency versus accessibility?
Let's say trusted, there is two kind of trusted setups. Let's say universal trusted setup and specific program setup. Running a trusted setup is a pain. I've been running a couple of them, and it's problematic. So something you want to avoid. Okay, so maybe it makes sense. We can go to Growth 16. It's still the optimal, very optimal. And if it's a circuit that really used many times and is very stable and it's very clear, then maybe it makes sense to run a ceremony for that.
Yeah.
For universal trusted setup, you need to run that. I think this is quite accepted that this is okay. Thinking getting that plonk, and so it's quite accepted. These ceremonies are I would say, that are, well, nobody doubts that these ceremonies are okay. And yeah, I mean, if and the perfect would be to go to untrusted setups. I mean, that would be the perfect scenario. But as far as I know, if you want to prove something that's untrusted on chain, this is quite expensive. I'm not aware of any good protocol that's able. I mean, the best thing is Plonk and requires a trusted setup.
I can share, like, yeah, so Mina, we have no trusted setup, but there is performance cost to doing that. We've decided to kind of eat that because it just makes the system that much more robust and not needing, you know, to run a whole trusted setup for the system. I think that, like, there's, I think, like, trusted setups, like pure trusted setups, like, I think can be a little concerning just because, like, if you have, like, a bug or something in what you've written, you can't really easily roll out an update. You have to run a whole nother trusted setup. Seems bad. I think there's a good case for universal trusted setups because in theory you run it once and then you're good to go. But I do think things should go towards, like, the trustless world. Like, I think you just need, like, a massive trusted setup to reach the kind of trust properties you would want in, like, a full system. Otherwise, that's just me for it. Yeah.
Yeah, super helpful. Thank you. I guess one of the main considerations or main things that we as observers kind of see is we see this kind of academic breakthrough, and the technical implementation will often kind of lag a little bit behind these academic breakthroughs. Could you give us a bit more of an insight into, I guess, why this might be, what some of the challenges in that sort of technical implementation of that academic breakthrough are, and just some of your general considerations when seeing and ingesting a new piece of literature?
Yeah, maybe I'll kick off because I'd be interested to hear from the other speakers. But to me, I kind of, that's not how it feels to me. Like, my background was physics, and I think before I left, it took more than a year to get my last paper from sort of it's done through it's published. And actually, I think we're in an industry where things are moving extremely quickly, and from new ideas to POCs, to me seems extremely fast, just relative to kind of other academic disciplines. Obviously, to get to a production system is a very different thing because, you know, like, these systems are managing lots of value. They can be hard to build, but they can be really hard to get to the level of confidence where you're ready to deploy it on mainnet, right? Like, building them is one thing, but then reaching that, like, okay, we're kind of really ready to trust hundreds of millions, billions of dollars to the system is a very different thing. Yeah, they can be hard to test in, you know, far harder than normal software. But yeah, the delta from, like, idea to POC to kind of people really starting to experiment in these, actually I think is quite fast. And but yeah.
Yeah, I mean, I would agree. I would say, like, there definitely is, like, a lag time to get into production. At least we see with us, though. I think particularly with what we often see is, like, because of how zero knowledge is so deeply integrated into Mina, when we change one thing, we have to start thinking about how that affects the rest of the system. And thinking about the upgrade paths for all those different parts gets more complicated. So we can have a POC, like, fast, but then it's like, how do you actually include that properly into the rest of the system? It's like a longer project. We did it recently with an upgrade to include some general purpose computation in the last year. And there's another wave of, like, folding and other things we're looking at now. But it does take a little bit of time to get it right in the production setting.
Yeah, I can explain a little bit the internals, but it's okay. There is papers appears almost like every week appears some interesting paper that you take a look and you read and you say, okay, this is promising or it's not promising. First thing is to understand the papers. Okay, so engineers that need to implement that, they need to understand the paper. Papers, they are not written in general to be understood for engineers. I mean, they are doing for their world. I mean, and are difficult even to study, to assimilate, to going to the point, and so it's I mean, it's a process of reading the right way. Then you need to select, and sometimes it's okay. Looks like a good idea, but needs to be proven. Well, first, the paper can be wrong. I mean, it needs to be reviewed, and maybe there is a lot of papers that they are just don't work, and so there needs a maturity people. But even okay, let's assume that this works and this is good. Then you need to You need to understand, you need to study, you need to implement. Also, you need to take some resources from the engineering teams. Engineering teams, I mean, they have some work to do, and there is the backlogs is full of things, and I mean, the market is pressing. So taking engineer time and putting to analyze some, I mean, do some implementation to check if that protocol, it improves or not improves, and then how much improves. I mean, you need to measure how much improves. So that makes the things, so you have some bandwidth on the engineering side, so you need to select where you are investing and which papers are you putting phase, and even that you can fail and would not be the first, second time, or third time that you implement some protocol or some idea. And in the moment that you are implementing, you realize that this doesn't work, or this works good here, but you have this other problem. I mean, you fix something, but it breaks another thing. I mean, it's not that simple. And if there is a good paper, in general, when there is a good paper, something that really makes sense and is very well explained, I agree that I think that this industry tends to implement it really fast. But really fast is not one. Do not expect that one paper appears one day and the next day there is an implementation. I only seen that once in crypto and was with Plonk. But besides that, I think it's the only paper that there was an implementation something like 1 week after the paper was released.
Yeah, makes sense. So we've spoken about different types of proving systems. Obviously, Polygon, Mina, ZK Sync all kind of take a different approach to proving in their stack. When you think about proving composability, and especially as ZK proofs become more and more used in applications and in production, do you think that composability of the ZK system itself matters, or is it the actual output and the system itself can be really anything?
Yeah, I'd like to see more composability between the different systems. Like, I think with Mina, we have a unique proof system. It's optimized for certain properties, but we want to be able to do more with, like, SP1 and other proof systems that are out there. At the moment, we did have a team that built out like a pretty large program that wraps Groth 16 and SP1 proofs into Mina. It's very slow, but it does the job, and you can run it server side, and it's okay. But I'd like to see more of it. Yeah.
ZKVMs will help a lot, because with ZKVM, actually, you can just take a verifier of any proving system and run it in a ZKVM. So composability is it's just it's something that you already have when just because you have a VM systems. If you go more low level, the big revolution of ZK of the last years, it has been very much the recursion part. Here is, Mina, I think, was the first one that were thinking in this idea of recursion in the blockchain and that. But verifying one proof in another proof, this has been always complicated in the snarks. But
let's go into this. I know we don't have a huge amount of time, but this was a question I was going to ask. The role of recursion has really come up in the past kind of 2-3 years. It kind of allows the stacking of proofs, so one proof to verify the validity of another proof. How does this fit in, and where does it actually kind of?
We have been using that from the first day. I mean, we are doing everything in Starks. Starks allows us to composite, to recurse and to build and to aggregate blocks and to do everything that we want. And in the last minute, we just take on a snark that is verifying a Stark. We're composing. So we are just taking one, and then that's why it's so cheap to verify that in Ethereum. This is an example of composability that we are using. But this idea, the idea is that you are taking the best system, the best proving system for verifying whatever you are interested on. Of course, you need to take into account the cost of this recursion, and this is where things matter. But in the case of Starks, proving a Stark in another Stark is quite, it's nice. It's nice. Starks work very well on that. Snarks is not that good.
Awesome. Sorry, please. I know we're coming up to time. I just wanted to finish on a more, I guess, tangible question for you guys. Are there any real-world examples of ZK proofs that really get you excited? Horizon applications that could really stand to benefit from ZK proof technology that really get you excited?
There are many. I could mention a lot. I mean, in the last panel, they are already talking about this identity in attestations and proving things and checking things. This is an important, really an important application. Privacy. But I would like to mention voting. I think that voting is an important, being able to organize voting systems without a central authority at large scale. I think this is an important application that the humanity needs. And this requires, of course, ZK, because the rest is privacy. And I mean, it's just one, but this is, for me, it's an important one.
Yeah.
You broadly agree, and then I also think as an industry we've got to do a better job of like telling people about ZK. You know, there's so many industries in the world that care about correct compute, right? When you think about things like healthcare systems, like autonomous systems, AI agents, flight systems, like there's a huge amount of work goes into things like formal verification, and to first approximation, I think a lot of people working in those industries still don't know what ZK is. So. Anywhere that you really want to think about, those guarantees that we know that ZK can offer, these industries, I think, still need some education. And even good friends that work in those spaces still kind of don't know what I do, at least.
Yeah, I mean, I think totally agree with all those. Like, I think I would just call back to like attestations is the one I'm particularly very excited about. Particularly like when you start combining other things, like private votes that are gated by attestations, for example, or attestations that gate like social networks or other kind of online or governance systems. Like that's where I start getting excited about some of the applications.
Awesome. Well, it looks like we're just at time, but thank you so much to our panelists for joining us. And yeah, thank you, audience, for listening to us ramble for 30 minutes. Appreciate it.